Alright, in this video we're gonna talk about the inverse Laplace transform. And just like derivatives, there's antiderivatives, which are the integrals. Here the same thing, there's Laplace transform and the inverse Laplace transform, the opposite of it. So if we got a capital F function, capital F, and obviously the Laplace of the capital F is small f, well, the same thing we could do is just the small of f, the inverse Laplace is equal to the inverse Laplace of capital F. It's just pretty straightforward. So I'm going to do an example here. So suppose that we've got f of s equals 1 over minus s minus 3 minus 16 over s squared plus 9. That's a 9, by the way. That's not well, that's not a g. So what we do is, well, we take the Laplace transform, the inverse, sorry, the Laplace transform of each piece individually, like we do in derivatives and the Laplace transform, because there's a minus sign. So the Laplace transform of both sides. So Laplace transform f of s equals the Laplace transform of that bit, s minus 3, and then minus the inverse Laplace transform of 16 over s squared plus 9. So, well, for this bit we're going to have to consult our table. You usually have to use our table, you just can't memorize them all. So yeah, in this bit we can look at this and see if anything matches up the formula. So that's going to be the inverse Laplace transform. So here we've got e to the power at equals 1 over s minus a. Here we've got a really similar one, which is 1 over s minus 3. So 3 is my a. So if 3 is my a, so the inverse of that is e to the power 3t. So and then minus, well, for this one we've got 16 over s squared plus 9. Well, in this case we've got a really similar one. Well, there's an s here, s over s squared, but there's no s in the numerator, so that's not our formula. Well, let's look at the sine at. Well, the sine at, we've got a squared over s squared plus a squared. A squared is a constant, by the way. We've got a constant in the numerator, but there's just one problem. Well, that's not actually, sorry, by the way, it's just an a. That's not actually, 16 is not the squared of a, so that's not actually our exactly the right formula, but it's very similar. What we do is going to manipulate this expression to make it equivalent to a. So basically the square root of 9 is this 3, so we're going to make the numerator of 3, right? So I'm going to rewrite this now. Instead of 9, I'm just going to write 3 squared, just to make it look like a squared. Well, the original numerator is actually 16, so I can't just make it 3. Well, but if we times 3 with 16 over 3, we'll get 16, right? So 3 over 3, 3 would cancel the 3, so we end up with this shape. But remember, in the Laplace transform, it's just like derivative. We can factorize the constants outside the Laplace, and that's exactly what I'm going to do here. And the reason why I'm doing this, well, first of all, I want to make the expression agree with the formula, with the table. And second, we can take the constants out, so that's exactly what I'm going to do. So what I'm going to do is e to the power 3t. Well, we already took the inverse Laplace of that, so, and I'm going to take 16 over 3 outside the inverse Laplace, and I'll take the inverse Laplace of my expression now. So well, we end up with 3 in the numerator, and denominator is just s squared plus 3 squared. So now I'm just gonna use the table. Now it agrees with the table. So a is gonna be the 3. So it looks like it, more like it now, right? So what I'm gonna do is inverse Laplace. We get sine. Well, instead of a, we get 3. So sine a3 t, sine 3t. Sorry. Oops, looks like I'm running out of space. I'm gonna have to use a different page. So I'm just gonna rewrite this. Minus 16 over 3 inverse Laplace of 3 over s squared plus 3 squared. Using the table, I'll take the inverse Laplace now. So by using the table, so 16 over 3, just looks very lousy, is going to times with sine 3t. So that's basically that's a 3 by this. It looks like a b, but it's not. It's a 3. So sorry about that. It's just a bracket for parentheses. So yeah. So that's the inverse Laplace of this function. Basically, that's just a really simple one. What you do is, well, if you look at the table, the formula, yeah, of Laplace, the table of Laplace, and if you find if it's similar, you just take the inverse Laplace. But if it's not, you kind of play around with it using algebra to make it agree or look like the one in the table, and then you take the inverse Laplace. So you can play with the constants only, but not the variables. That's just a simple one. Obviously, in the future, you're going to face Laplace or the inverse Laplace using partial fractions and that, and we'll cover that in the future videos.